the next important thing is how to test your new designs. Well, the first step is to build the models in CAD, which I think many people are quite proficient. How much time will it take to run? Well, if you're doing a steady state simulation, these type of, if you run it on such powerful computers, you should be able to get the results in 1 to 2 days. So how to test new designs? So you build your CAD models and you extract the wet volume. Now remember, what is the wet volume? Wet volume is the surfaces or parts that are touching the fluid. Anything that interacts with the fluid should be included. And then you need to retain the part separately in the CFD. If you don't do that, then what's going to happen? Then it's going to actually give you the drag forces for the entire model and not just for that particular wing. Then you need to put the model in the virtual wind tunnel and then apply the boundary conditions. Okay, and I'll show you a demonstration of this after I finish the presentation. So at this point, I'm kind of doing it in reverse. So basics of CFD. So CFD, in general, there is 4 processes: pre-processing, meshing, solving, and post-processing. If you want to do a good job in CFD, you need to be aware of all these 4 concepts. If you don't, then you're kind of not being thorough. So what is CFD all about? Well, CFD is all about solving some fundamental equations. So these equations are partial differential equations. They are nonlinear. And these are the minimum set of equations that you need to solve. Now remember, your computer cannot solve partial differential equations. So you take these equations and you convert it into a form so that you can solve it on a computer. This process is called as discretization. So what you do is you create these small volumes. So for example, here you can see that there's a square here, there's a square here, there's a smaller square here, and an even more smaller square here. So what you're doing is you're taking all these equations and you're solving it inside that particular cell. And when you solve it, you will get the value for rho, which is the density, u component of velocity, v component of velocity, w, and the total energy. So similarly, when you calculate these components in one cell, you do the same thing again and again in all the cells, and that is what you call as a CFD simulation. Now, since these are partial differential equations, you need initial conditions and boundary conditions. The more the number of equations that you have, the more boundary conditions that you have to provide. The fewer the equations that you have, the fewer the boundary conditions. I hope that makes sense. Now, in addition to this, you need a turbulence model. Why? If you take these equations as it is, and if you try to simulate fluid flow, you will get the right answer. Don't get me wrong. But if you have to predict the boundary layer correctly, then the amount of computational mesh points will be very huge. It is so huge that if you run the simulation on a F1 car with that many amount of cells, your simulation would run for literally several years. I'm not joking, or I'm not making this up. So that type of simulation is called as the direct numeric simulation. The number of computational cells that you need is roughly Reynolds number to the power 3. In your wind tunnel simulations, your Reynolds number is roughly 1 lakh. So that's basically 10 power 5. So 10 power 5 to the power 3 is 10 power 15, right? So that is 10 power 6 billion cells. 10 power 6 billion cells. That is, I think, the largest simulation, computational fluid dynamics simulation that has ever been attempted was maybe 100 million or 200 million, maybe somewhere around that, maybe slightly more. So if you can never run such a simulation by solving these equations directly. So what you do is you basically model the turbulence. You approximate the turbulence using an approach called as the RANS approach, Reynolds Average Navier-Stokes. When you do that, you basically get 2 equations that you have to solve, which are K and epsilon. So when you see K and epsilon, right, that is what it means. When you solve K and epsilon, you get something called as nu T, which is your turbulent viscosity. And finding the nu T is basically the problem of turbulence modeling. All the different turbulence models that you might have heard of, K epsilon, RNG K epsilon, rapid distortion K epsilon, K omega 2006, K omega 2009, K omega SST. All of these models have a different way of calculating nu T. When you calculate the turbulence viscosity, you can calculate your entire solution. Calculating this nu T is the art of turbulence modeling. So you need to use a turbulence model. That is kind of the short story.